What if everything around you, the chair you're sitting on, the air you're breathing, even the screen in front of you, wasn't as solid or predictable as it seems? What if, deep down at the smallest scales of existence, reality itself is bubbling like a cosmic soda, fizzing with chaotic energy and infinite possibilities? This isn't science fiction. It's the mind-bending world of quantum foam, the turbulent foundation of reality that physicists believe underlies the very fabric of space and time. Picture this: you're standing at the edge of a stormy ocean, watching waves crash unpredictably against the shore. Now imagine that same chaos, but on a scale so tiny, it makes an atom look gigantic. That's quantum foam. It's a seething, frothing sea of energy at the heart of existence, where particles flicker in and out of existence in the blink of an eye, and the rules of physics as we know them start to unravel. This isn't just a curiosity for scientists in lab coats. It challenges everything we think we understand about how the universe works, from the way gravity operates to the very nature of reality itself. So why should you care? Because quantum foam isn't just some abstract idea locked away in textbooks. It's the hidden engine behind some of the most profound mysteries of our cosmos. Black holes, dark energy, even the birth of the universe, they all connect back to this turbulent subatomic realm. And what we're about to explore could reshape how you see the world, right down to the space between your fingertips. Strap in, because we're diving into the stormy depths of quantum foam, where the ordinary rules don't apply, and the universe is far stranger and more beautiful than you ever imagined. Back in the 1950s, physicist John Wheeler peered into the bizarre depths of quantum mechanics and had a revelation that would shake our understanding of reality. He realized that when you zoom in far enough, past atoms, past particles, even past the tiniest bits of matter, space and time themselves stop behaving like the smooth, predictable fabric we're used to. Instead, they churn and twist like a boiling pot of water, a chaotic dance Wheeler called quantum foam. Imagine trying to measure the surface of a lake during a hurricane. Your ruler would jump and twist with every wave, making precise measurements impossible. Now shrink that lake down to sizes so small they're almost incomprehensible. Think a millionth of a billionth of a billionth of a centimeter. At that scale, known as the Planck length, the rules of Einstein's general relativity collide violently with the uncertainty of quantum mechanics. Gravity warps space, particles flicker in and out of existence, and spacetime itself becomes a seething, frothing mess of virtual particles and microscopic black holes blinking into reality before vanishing again. Wheeler's insight was revolutionary because it showed that the universe isn't built on solid, unchanging ground. Instead, the foundation of everything is more like a stormy ocean, constantly shifting and bubbling with energy. Picture pouring soda into a glass, those tiny, fizzy bubbles popping at random. That's quantum foam, but instead of carbonation, it's made of spacetime itself, warping and reforming in unpredictable bursts. This idea didn't just come from abstract math. Wheeler was wrestling with a fundamental problem: how to reconcile Einstein's smooth, warping space-time with the chaotic, probabilistic world of quantum particles. The answer: at the smallest scales, the universe doesn't pick one or the other, it embraces both, creating a turbulent, ever-changing foam where the very concepts of here and now start to lose meaning. And here's where it gets even stranger. Some theories suggest that quantum foam might hold the key to phenomena we still can't fully explain, like dark energy accelerating the universe's expansion or the mind-bending physics inside black holes. If Wheeler was right, then every inch of empty space around us isn't empty at all. It's a frenetic, boiling sea of potential, hidden just beneath the surface of what we can perceive. To grasp just how mind-bogglingly small the quantum foam gets, we need to talk about the Planck length, the universe's ultimate limit on smallness. Think of it as reality's pixel size, roughly 100 trillionth of a trillionth the width of a single atom. At this unimaginable scale of 10 to the minus 35 meters, the smooth, continuous space we move through every day shatters into something far stranger, a churning sea where gravity and quantum mechanics wage an endless tug of war. Zoom in on your phone's screen and eventually you'll see individual pixels, tiny blocks of color that form the image. Now imagine zooming in on spacetime itself until you hit its pixels. Except instead of neat squares, you'd find a frenzied storm. Particles wink in and out of existence, microscopic black holes form and evaporate in instants, and even concepts like distance and time lose their meaning. This is where physics as we know it hits a wall. Einstein's relativity paints spacetime as a smooth fabric bending under gravity, while quantum mechanics insists everything is inherently fuzzy and uncertain. At the Planck length, these two titans of physics collide, leaving us with quantum foam, a realm where the very ground rules of reality dissolve into chaos. Here's the wild part: we can't even observe this directly. The energy needed to probe such tiny scales would be so immense, it'd create a black hole on the spot. So instead, physicists rely on math and sheer imagination, piecing together clues from black hole thermodynamics, particle collisions, and cosmic radiation. What they've found suggests that quantum foam isn't just turbulence, it's the universe's raw creative engine, those fleeting particles and warps in space-time. They might hold the keys to everything from dark energy's mysterious push to the holographic nature of reality itself. So next time you glance at a calm lake or a still night sky, remember, beneath the surface, down where even atoms seem gargantuan, the universe is fizzing with infinite possibility. The foam is always there, hidden in the silence between moments, rewriting the rules of existence one Planck-length bubble at a time. If you've ever watched popcorn kernels burst unpredictably in a hot pan, you've already glimpsed the bizarre behavior of quantum foam. At its core, this churning sea of spacetime isn't empty, it's teeming with virtual particles, fleeting pairs of matter and antimatter that erupt into existence before vanishing again like microscopic fireworks. These particles don't just appear randomly, they're borrowing energy from the vacuum itself, a cosmic loan that must be repaid almost instantly. Think of it like tapping your neighbor for a cup of sugar, only to return it before they even notice it's gone. Richard Feynman, the legendary physicist, captured this chaos in his famous diagrams where particles zigzag like tangled spaghetti strands. Picture one of those diagrams side by side with popcorn popping. Both are eruptions of energy, both unpredictable, both over in a flash. The difference: virtual particles aren't just a snack. They're the universe's way of testing the limits of reality, constantly probing what's possible within the razor-thin margins allowed by quantum uncertainty. Here's where it gets even wilder. These particles aren't just theoretical, they leave fingerprints. Take the Casimir effect. Place two metal plates incredibly close together in a vacuum, and they'll slowly be pushed together. Why? Because the space between them is so narrow, only certain virtual particles can fit, while the bustling foam outside continues unchecked. The result: an invisible force like a cosmic crowd shoving the plates together, proving the foam's activity isn't just math, it's measurable. But the real kicker: these fleeting particles might hold the secret to one of the universe's biggest mysteries, dark energy. Some theories suggest that the endless popping and fizzing of virtual particles in the quantum foam could be fueling the accelerating expansion of the cosmos. It's as if every cubic inch of empty space contains a tiny engine humming with borrowed energy, pushing the universe apart one Planck-length burst at a time. So next time you see steam rising from your coffee or bubbles dancing in a soda, remember, you're witnessing a faint echo of the quantum foam's endless creativity. The universe isn't just built on particles and forces, it's built on borrowed moments, a cosmic dance of existence and erasure happening everywhere all the time, hidden just beneath the surface of the ordinary. Imagine trying to take a photo of something so small, your camera flash would actually destroy the very thing you're trying to see. That's essentially the predicament we face when probing the quantum foam, thanks to a cosmic rulebook written by two giants of physics, Werner Heisenberg and Albert Einstein. Heisenberg's uncertainty principle tells us there's a fundamental limit to how precisely we can measure anything at the quantum level. The more accurately you try to pin down a particle's position, the more wildly its momentum fluctuates, like trying to catch a hummingbird in total darkness. The moment you feel its wings, it's already gone somewhere else. Now combine this with Einstein's revelation that energy warps spacetime, and you've got a recipe for scientific fireworks. Picture building a microscope so powerful, it could peer down to the Planck length where quantum foam churns. To see details that tiny, you'd need photons with unimaginable energy particles packing so much punch, their very mass would curve spacetime like a bowling ball on a trampoline. And here's the cosmic joke: focus that much energy into such a tiny space, and you'd inevitably create microscopic black holes right where you're trying to observe. It's like trying to study soap bubbles with a blowtorch. Your measurement tool becomes the instrument of destruction. This isn't just theoretical. In 2009, physicists at the LHC feared their own particle collisions might briefly spawn black holes. They didn't, but the math suggested it was possible at extreme energies. At Planck scale resolutions, every observation becomes a violent act. The universe seems to be saying, you can look but stare too hard, and reality itself crumbles under your gaze. What's truly fascinating is how this connects to the holographic principle, the idea that all the information in a volume of space might actually be encoded on its surface. Quantum foam's turbulence suggests spacetime might be pixelated at fundamental levels, with each pixel carrying bits of information like a cosmic QR code. Trying to zoom in beyond the Planck length would be like enlarging a digital photo until all you see are blurry squares. Except in this case, the squares are roiling bubbles of spacetime itself. So where does this leave us, staring at nature's ultimate "do not disturb" sign? The quantum foam isn't just unpredictable, it's fundamentally unobservable at full resolution, protecting reality from the paradoxes that would arise if we could see past the veil. Like an artist's canvas viewed through frosted glass, the universe teases us with glimpses of its underlying texture while keeping its deepest secrets just out of focus. John Wheeler didn't just stop at describing quantum foam as a turbulent sea. He took the idea even further, suggesting that within this chaotic froth, spacetime might occasionally twist itself into microscopic wormholes, fleeting tunnels connecting distant points in the blink of an eye. Imagine stirring a pot of boiling water, watching bubbles rise, collide, and merge for just an instant before bursting apart. Now replace those bubbles with tunnels through spacetime itself, forming and vanishing so quickly they're gone before even light could traverse them. That's Wheeler's vision: wormholes bubbling up from the quantum foam like cosmic soap bubbles, each one a shortcut through the fabric of reality. But don't pack your bags for interstellar travel just yet. These wormholes would be unimaginably tiny, far smaller than an atom, and staggeringly unstable. Picture a tunnel made of spun sugar dissolving the moment it forms. The energy required to keep one open longer than a Planck time, that's 10 to the minus 43 seconds, would be so immense it'd collapse under its own gravitational pull, snapping shut like a mousetrap. Even if you could find one, trying to pass through would be like threading a needle with a rope during an earthquake. Here's where it gets even more fascinating. These wormholes wouldn't just be quirks of math, they might solve deep mysteries in physics. Take black holes, for example. When one evaporates via Hawking radiation, where does all its information go? Some theorists suggest it could be encoded in these microscopic wormholes, threading through the quantum foam like invisible stitches holding spacetime together. Others propose they might explain entanglement, that spooky connection between particles across vast distances. Could entangled particles be linked by Planck-scale wormholes too small to see? It's a wild idea, but in the froth of quantum foam, even the wildest ideas get a chance to bubble up. The kicker, we might never directly observe these wormholes. They'd flicker in and out of existence faster than any instrument could detect, leaving only subtle traces in the equations. But their theoretical existence hints at something profound, that deep down, spacetime isn't just curved or warped. It's alive, constantly rewriting its own rules, stitching itself together in ways we're only beginning to imagine. So while we can't surf these quantum tunnels yet, their fleeting existence reminds us that the universe is far stranger and more inventive than our boldest science fiction. We think of time as a steady river flowing from past to future, but what if, deep down, it's more like a flickering film reel with missing frames? Quantum foam doesn't just warp space, it shakes the very foundations of time itself, suggesting our smooth, unbroken experience of moments might be an illusion. Picture a flipbook animation where every page turns smoothly to create the illusion of motion. Now imagine randomly tearing out some of those pages. The animation still plays, but with subtle jumps and gaps, tiny moments that simply vanish. That's the mind-bending possibility of granular time, where the universe operates not as a continuous flow, but as a series of Planck-sized ticks, each lasting about 10 to the minus 43 seconds. At this unimaginably brief scale, time might not even exist between those ticks. It's like watching a digital clock. The numbers change in clear jumps with no movement in between. We perceive time as fluid because our brains can't possibly process intervals this short. But in the quantum foam, where space-time churns like boiling water, these gaps could allow for bizarre phenomena. Particles might briefly skip across moments, appearing to teleport. Causality, the rule that effects must follow causes, could wobble like a table with uneven legs. Even the order of events might blur with microscopic time glitches, where the sequence of before and after becomes negotiable. The implications ripple outward. If time is granular, then black holes where gravity stretches time to its limits might reveal these missing frames near their event horizons. Some theories suggest that Hawking radiation, the slow leak of energy from black holes, could carry echoes of these time fluctuations like static from a corrupted video file. Even our GPS satellites, which rely on ultra-precise timekeeping, must account for Einstein's time dilation. But what if quantum time gaps introduce tiny errors we haven't even detected yet? Here's the real twist. If time isn't continuous, then the present moment isn't a razor-thin slice between past and future. It's more like a pixel in a cosmic movie, surrounded by gaps we'll never perceive. The universe might not render every moment in sequence, but instead jump between quantum states, leaving the in-between to imagination. So the next time you check your watch, remember, those steady ticks are hiding a storm of chaos beneath, where time itself stutters, skips, and rewrites its own rules. Black holes aren't just cosmic vacuum cleaners, they're the universe's most efficient librarians, meticulously recording every bit of information that crosses their event horizons. But here's the puzzle. How can something so dense and destructive preserve information so perfectly? The answer might lie in the quantum foam's chaotic dance, where spacetime's turbulence could be encoding secrets in ways we're only beginning to decipher. Picture a black hole's event horizon not as a smooth, two-dimensional surface, but as a seething, pixelated boundary where each Planck-sized patch flickers with quantum foam. Stephen Hawking stunned the world when he calculated that black holes emit radiation and slowly evaporate. But this raised a terrifying question. If a black hole vanishes, what happens to all the information it swallowed? Quantum mechanics insists information can't be destroyed, yet general relativity suggests it's gone forever. This paradox haunted physicists for decades until they realized the answer might be written in the foam. Think of the event horizon as a hologram projecting a three-dimensional reality from a two-dimensional surface. Now imagine that surface isn't static, it's a storm of quantum foam, where microscopic wormholes and virtual particles constantly rearrange spacetime's fabric. Every particle, every atom that falls into the black hole leaves an imprint on this frothy boundary, like a fingerprint pressed into wet sand before a wave washes it away. The foam's chaos doesn't erase the data, it scrambles it into a quantum code so intricate it'd take the universe itself to decode it. Here's where Hawking's entropy calculations get wild. Entropy measures disorder, and black holes have an enormous amount of it proportional to their surface area, not their volume. This hints that all the information inside could be stored on the horizon surface, pixelated by the foam's turbulence. It's like compressing an entire library into the etchings on a single grain of rice. The quantum foam's frenetic activity ensures no data is lost, just transformed into a language we don't yet understand. The holographic principle takes this further, suggesting our entire universe might work the same way, a three-dimensional projection of information stored on some distant two-dimensional surface. If true, then quantum foam isn't just background noise. It's the universe's projector, flickering reality into existence one Planck-length bubble at a time. So next time you hear about a black hole's mysteries, remember, its secrets aren't lost in the darkness. They're etched into the foam, swirling in the chaos, waiting for physics to catch up and read the story written in spacetime storm. The Casimir effect is like catching the quantum foam red-handed. The moment this frothy, chaotic realm leaves its fingerprints on reality, picture two ultra-thin gold plates hanging parallel in a vacuum, separated by a gap smaller than the width of a human hair. At first, nothing happens, but as you narrow that gap to within a few millionths of a meter, something eerie occurs. The plates suddenly snap together as if pulled by invisible hands. This isn't magic, it's the quantum foam's turbulence playing out in real time, and it's one of the few ways we can indirectly observe the universe's frenetic undercurrents. To understand why those plates move, imagine standing in a crowded subway during rush hour. People jostle in all directions, pushing randomly against you. But if someone suddenly positions two walls very close together, only a few people can fit between them while the chaotic crowd continues pressing from the outside. The result, the walls get shoved inward by the imbalance of forces, a perfect analogy for what happens in the quantum foam. In the vacuum of space, virtual particles constantly flicker in and out of existence, borrowing energy from nothingness before vanishing again. Normally, this chaos is symmetrical particles pop up everywhere equally, cancelling each other out. But when two plates are brought extremely close together, only certain wavelengths of virtual particles can fit between them, while outside the plates, the quantum foam continues its unbridled dance. This imbalance creates a pressure difference, pushing the plates together with measurable force. Scientists first predicted this effect in 1948. But it wasn't until the late 1990s that lab experiments captured it with breathtaking precision. In slow-motion footage, you can see the gold plates, held apart by delicate springs, suddenly lurch together as the gap narrows, a visible testament to the unseen quantum storm raging around us. What makes this phenomenon even more astonishing is its scale. The force between the plates is minuscule, about the weight of a single ant's leg. Yet it emerges from the collective might of countless virtual particles appearing and vanishing trillions of times per second. If you could shrink yourself down to the size of an atom and peer into that gap, you'd witness a microscopic maelstrom, particles flashing into existence for mere instants before winking out, their fleeting lives nudging the plates ever closer. But the Casimir effect isn't just a quirky lab demonstration. It hints at something far grander. The quantum foam's energy might be shaping the universe in ways we're only beginning to grasp. Some theories suggest that if we could manipulate these vacuum fluctuations, We might one day harness them for propulsion or even energy generation, tapping into the universe's own restless motion. For now, though, those gold plates remain our best window into the invisible storm, a fleeting glimpse of the chaos that underpins everything. At first glance, quantum foam and string theory might seem like two sides of the same cosmic coin, both attempting to explain the deepest workings of reality. But zoom in closer, and you'll find they're as different as a roaring thunderstorm and a symphony orchestra. Quantum foam is chaos incarnate, a churning sea where particles erupt and vanish like bubbles in boiling water. String theory, on the other hand, paints a picture of elegance and order, where the universe hums with the harmonious vibrations of impossibly tiny strings. Picture this split screen. On one side, a pot of overcooked spaghetti noodles tangled in every direction, twisting and snapping at random. That's the quantum foam, where space-time itself is a turbulent mess of fleeting particles and microscopic black holes. Now flip to the other side, where a guitarist plucks a string, sending a perfect wave rippling along its length. Each vibration corresponds to a different particle and electron, a quark, even gravity itself, all united by the same underlying melody. That's string theory's vision, not chaos but music. The difference isn't just philosophical, it's mathematical. Quantum foam emerges from the clash between general relativity and quantum mechanics, where gravity's smooth curves collide with the jagged uncertainty of particles. The result, a frothy mess where even time and space lose their meaning. String theory, meanwhile, smooths over these contradictions by proposing that everything, every force, every particle, is woven from incredibly tiny, vibrating strings. Instead of point-like particles smashing together unpredictably, you have strings merging and splitting like notes in a chord progression. But here's where things get fascinating. These two perspectives might not be as opposed as they seem. Some theorists suggest that quantum foam could be the low-resolution view of reality, while string theory describes the finer details, like how choppy ocean waves resolve into individual water molecules when you zoom in close enough. Others propose that the foam's turbulence might actually be the collective vibration of countless strings, the way random heat in a room emerges from the orderly motion of atoms. The real tension lies in how each theory handles gravity. Quantum foam treats gravity as a distortion of spacetime warped by the foam's chaotic energy. String theory, however, encodes gravity as just another vibration, the deepest note in the universe's song. If quantum foam is a storm, string theory is the weather report, trying to predict the tempest through equations. Yet for all their differences, both theories agree on one thing: the universe isn't what it seems. Whether it's the dissonance of the foam or the harmony of strings, reality is far stranger and more wondrous than our everyday experience suggests. And somewhere between the tangled spaghetti and the singing strings, the truth might be waiting just out of reach. Dark energy, the mysterious force accelerating the universe's expansion, might not come from some exotic new particle or undiscovered law of physics. Instead, it could be bubbling up from the quantum foam itself, a cosmic byproduct of spacetime's endless churn. Picture blowing up a balloon covered in swirling foam, each bubble popping and reforming as the surface stretches. Now imagine that balloon is the universe, and the foam isn't just decoration, it's the engine driving the expansion. At the heart of this idea lies a startling possibility: the vacuum of space isn't empty. Quantum foam ensures it's seething with energy, virtual particles flashing in and out of existence like sparks in a cosmic forge. Normally, these fleeting particles cancel each other out, leaving no net effect. But what if, on the grandest scales, they don't? Some calculations suggest that the foam's relentless activity could generate a repulsive force, a kind of anti-gravity pushing galaxies apart. It's like blowing up that balloon while tiny, unseen hands keep adding more air, stretching the fabric faster and faster. Here's where the analogy gets even richer. Just as foam on a balloon's surface changes as it expands, bubbles merging, popping, or stretching into new shapes, quantum foam's behavior might shift as the universe grows. Early on, when everything was denser, the foam's energy could have been negligible, drowned out by the heat and pressure of the Big Bang's aftermath. But as space stretched and matter thinned, that same frothy turbulence might have emerged as the dominant force, like whispers becoming audible only when the room falls silent. Critics argue this can't be the full story. Simple estimates of the foam's energy predict a value astronomically larger than what dark energy observations show, a discrepancy so huge it's been called the worst theoretical prediction in physics. Yet some theorists aren't ready to dismiss the connection. They propose that unknown symmetries or cancellation mechanisms might be at work, taming the foam's wild energy into the subtle push we observe. Others suggest dark energy isn't constant, that the foam's influence ebbs and flows over cosmic time, leaving traces in the way galaxies cluster or supernova brighten. What's undeniable is the poetry of the idea that the largest phenomenon in the universe, its accelerating expansion, might owe itself to the smallest, most turbulent corners of reality. Every cubic centimeter of empty space, no matter how serene it appears, could be a microcosm of creation and destruction, its energy quietly shaping the fate of everything. So when astronomers peer into the night sky, measuring galaxies racing away, they might not just be observing the universe's expansion, they're glimpsing the quantum foam's handiwork written across the cosmos in streaks of starlight. If quantum foam is the universe's chaotic heartbeat, then time crystals are its precise, rhythmic pulse. These bizarre structures, first theorized in 2012 and later created in labs, aren't just another state of matter. They're a defiance of everything we thought we knew about time and symmetry. Picture a snowflake that doesn't just repeat in space but in time, its structure cycling endlessly without energy input, like a clock that ticks forever without winding. That's the essence of a time crystal, a system locked in an eternal loop, echoing the quantum foam's dynamism but with eerie, perfect order. In a groundbreaking MIT experiment, scientists used flashing lasers and precisely tuned microwave pulses to coax a chain of trapped ions into this strange state. The result, a shimmering dance of particles pulsing at intervals that couldn't be explained by ordinary physics. The ions didn't just react to the lasers, they synchronized into a rhythm twice as slow as the pulses driving them, as if the material itself had developed a stubborn sense of tempo. This wasn't just energy being transferred, it was symmetry breaking on a fundamental level, with time itself becoming the stage for a new kind of order. What makes time crystals so fascinating is how they mirror quantum foam's restless creativity while flipping the script. The foam is all about chaotic, spontaneous fluctuations, particles blipping in and out of existence with no pattern. Time crystals, though, are the opposite. They're rigidly periodic, repeating their structure not just in space but across time, like a drumbeat woven into the fabric of reality. Yet both phenomena share a profound connection. They reveal that the universe isn't just made of matter and energy, it's also built on rhythm and renewal, whether in the foam's turbulent froth or a crystal's metronomic stability. Here's where it gets even wilder. Time crystals don't just challenge our understanding of matter, they hint at entirely new phases of existence, ones that could rewrite the rules of thermodynamics. Normally, perpetual motion is impossible, energy always dissipates, but time crystals sidestep this by existing in a stable, out-of-equilibrium state. They're not creating energy, they're recycling it, like a dancer spinning on frictionless ice. Some theorists speculate that if quantum foam is the universe's raw static, time crystals might be the first notes of a deeper cosmic symphony, one where time itself has texture and structure. The implications ripple far beyond the lab. If we can harness time crystals, they might revolutionize quantum computing, acting as ultra-stable frameworks for qubits. Or perhaps they'll unlock new ways to study black holes where time bends to its limits. But for now, their greatest gift is perspective, a reminder that beneath the surface of the ordinary, reality is stranger, richer, and more rhythmic than we ever dreamed. Just as the quantum foam churns unseen, time crystals pulse in quiet defiance, proof that the universe loves a pattern, even in its most hidden corners. Einstein's general relativity paints gravity as the smooth warping of spacetime, a cosmic trampoline bending under the weight of stars and planets. Meanwhile, quantum mechanics tells us that at the smallest scales, reality is a frenzied storm of probabilities, where particles pop in and out of existence like fireflies in a hurricane. The problem: these two titans of physics refuse to play nice when it comes to the quantum foam, the chaotic, frothy foundation where spacetime itself dissolves into turbulence. It's like trying to merge a Renaissance masterpiece with a Jackson Pollock painting. The brushstrokes just don't line up. Imagine handing Einstein and Schrödinger a jigsaw puzzle, only to realize the pieces are cut from entirely different universes. On one side, Einstein's pieces are curved and continuous, depicting gravity as a serene landscape of rolling hills. On the other, Schrödinger's fragments are jagged and fragmented, shimmering with uncertainty. The quantum foam is where these pieces collide, creating a paradox that stumped physicists for nearly a century. How can gravity, so elegant in its spacetime geometry, survive in a realm where here and now flicker like a candle in the wind? The heart of the conflict lies in the Planck scale, where the foam's turbulence reaches its peak. Here, general relativity predicts spacetime should warp smoothly, like a silk sheet draped over a sphere. But quantum mechanics insists that at these scales, the sheet is more like a tangled net, riddled with holes and frayed edges. Throw in Heisenberg's uncertainty principle, and the fabric of reality starts to look like a fraying sweater. Pull one thread and the whole thing unravels. Attempts to reconcile these worlds have birthed some of the most ambitious theories in physics. String theory suggests gravity might be carried by tiny, vibrating loops threading through the foam's chaos. Loop quantum gravity proposes spacetime itself is woven from discrete, interlocking threads like a cosmic chainmail armor. Even holographic principles get in on the action, implying the foam's turbulence could be a projection of deeper, hidden dimensions. Yet none have fully bridged the gap. It's as if we're trying to translate a poem written in two languages at once. The meaning keeps slipping through our fingers. The stakes couldn't be higher. Until we crack this puzzle, black holes remain paradoxical. The Big Bang's origins stay shrouded, and dark energy keeps its secrets. The quantum foam isn't just a scientific curiosity, it's the battlefield where the future of physics will be decided. Every equation scribbled, every experiment conducted, brings us closer to a theory that might finally stitch these mismatched pieces into a coherent whole. Until then, the foam keeps churning, whispering riddles in the language of the universe itself. Rewind the universe back to its first fiery moments, and you might find that the Big Bang wasn't an explosion in empty space. It was a cataclysmic eruption of space itself, born from a supercharged quantum foam hotter than any star. Picture a cauldron of spacetime, not simmering, but roaring at temperatures beyond comprehension. Every Planck-sized bubble a potential universe bursting into existence. In this primordial frenzy, gravity hadn't yet settled into the familiar force we know. It was just another tremor in the foam, twisting and knotting as spacetime struggled to define itself. This isn't just poetic imagery. The math suggests that at these energies, the universe's very structure would have been indistinguishable from quantum foam, a seething plasma where particles and forces blurred into a single, seething whole. Imagine tossing a handful of sand into a whirlwind, each grain a flickering particle, the wind itself the fabric of spacetime, churning too violently for anything stable to emerge. That's the infant universe, not smooth, not orderly, but a fractal storm where every fluctuation could have birthed an entire cosmos. Now here's the twist. Some models propose that what we call the Big Bang might have been a phase transition, a moment when the quantum foam's turbulence finally, cooled enough for spacetime to crystallize into something recognizable. Think of water freezing into ice, chaotic molecules suddenly locking into a lattice. In the universe's case, the foam's froth didn't vanish. It simply stabilized, leaving behind traces of its chaos in the cosmic microwave background. The afterglow of creation, where tiny temperature variations echo the foam's primordial ripples. And those galaxies we see today, they might be the descendants of spacetime bubbles that grew exponentially during inflation, stretched from quantum-scale quirks to cosmic vastness. Like soap bubbles in a sink merging into larger clusters, regions of the foam that happen to be slightly denser pulled in more matter, seeding the galaxies, stars, and planets we now call home. The foam's randomness, frozen in that first second, became the blueprint for everything. This vision reshapes how we see existence. The universe wasn't born in emptiness, it was forged in turbulence, its structure imprinted by quantum foam's fleeting asymmetries. Even now, in the quiet between stars, that primordial froth lingers. The Big Bang wasn't the beginning, just the moment the foam's chaos became a canvas and the universe began painting itself into being. Deep beneath the Antarctic ice, scientists are hunting ghosts, not the supernatural kind, but the most elusive particles in the universe. Neutrinos, nearly massless and barely interacting with matter, streak through the planet like cosmic phantoms, untouched by magnetic fields or solid barriers. But here's where it gets fascinating. When these ultra-high-energy neutrinos travel billions of light-years across the cosmos, they might carry scars from their journey through the quantum foam, their properties subtly scrambled by spacetime's turbulent undercurrents. Think of it like mailing a pristine white shirt across the world, only to find it arrive splattered with ink. The stains aren't random, they're a map of every obstacle the package encountered. Similarly, neutrinos born in distant supernova or active galactic nuclei should reach Earth in predictable states unless they've been jostled by the quantum foam's froth along the way. At energies exceeding 1 quintillion electron volts, these particles could interact with spacetime's Planck-scale bubbles, their quantum flavors shifting unpredictably like colors in a spinning kaleidoscope. This is where IceCube, the world's most unusual telescope, comes in. Buried a mile beneath the South Pole, its grid of over 5,000 optical sensors monitors a cubic kilometer of ultra-clear ice. When a neutrino occasionally collides with an atomic nucleus, it creates a secondary particle that moves faster than light in ice, though still slower than light in a vacuum, emitting a faint blue glow called Cherenkov radiation. The result, streaks of light frozen in the ice like minuscule lightning bolts, their angles and intensities encoding the neutrino's original energy and flavor. By analyzing thousands of these events, physicists hope to spot anomalies, patterns that can't be explained by standard particle physics. Imagine catching a musician playing the wrong notes in a symphony. Those mistakes could reveal the foam's hidden structure. Some models suggest high-energy neutrinos might experience microscopic time delays or quantum decoherence, as if spacetime itself briefly tangled their signals. Others propose that certain flavors might arrive in unexpected ratios, hinting at unseen interactions with the foam's fleeting wormholes or virtual black holes. The challenge is separating cosmic noise from quantum whispers. IceCube's data must be sifted with machine learning algorithms trained to spot statistical deviations. It's like listening for a faint radio station through static, except the static is the universe's background chatter, and the station might be broadcasting from the foam. What's at stake? If successful, neutrino astronomy could give us the first indirect image of quantum foam structure, proving that spacetime isn't smooth but pixelated. It's the ultimate cosmic detective story, particles as messengers, ice as a lens, and the universe's most chaotic layer hiding in plain sight. Every streak of light in the Antarctic deep is a potential clue, waiting to crack open reality's stormiest secret. Science fiction has a knack for taking the weirdest corners of physics and spinning them into gripping tales, and quantum foam is no exception. From Star Trek's subspace to Doctor Who's time vortex, the foam's chaotic energy has inspired some of the most iconic visuals in sci-fi history. Remember those scenes where starships shudder violently as if hitting invisible speed bumps? That's Hollywood's take on quantum turbulence, a dramatization of spacetime's hidden storm. Take Star Trek's warp drives, for instance. When the Enterprise engages its engines, it's not just speeding through empty space, it's navigating the frothy layers of subspace, a realm where quantum foam's turbulence becomes a navigational hazard. The show's technobabble about gravimetric distortions and subspace fractures isn't pure fantasy. It echoes real theories about how quantum foam might warp spacetime at microscopic scales, creating pockets of instability. In one memorable episode, the crew encounters a subspace rift that behaves eerily like a magnified version of Wheeler's wormholes, fleeting tunnels in the foam that could theoretically connect distant points in space. Then there's Doctor Who's time vortex, a swirling, chaotic ribbon of colors that the TARDIS barrels through like a surfer riding a cosmic wave. The vortex isn't just a pretty visual effect, it's a poetic exaggeration of quantum foam's time-bending potential. If time truly stutters at Planck scales, as some theories suggest, then the vortex's erratic flow mirrors how moments might splinter and reconnect in the foam's depths. Even the TARDIS' infamous rough landings, those jolting arrivals that send the Doctor tumbling, could be nods to spacetime's granularity, as if the ship's traversal through the vortex occasionally snags on the foam's turbulent texture. But sci-fi doesn't just borrow from physics, it amplifies it. Imagine a spaceship hitting quantum turbulence so severe, the crew starts experiencing time out of order, or worse, fragments of alternate realities bleeding into their own. Films like Event Horizon and Interstellar flirt with these ideas, turning the foam's unpredictability into existential horror. One moment you're cruising through space, the next your ship's hull is groaning under forces that shouldn't exist, as if spacetime itself has teeth. What makes these tropes so compelling is their grain of truth. While we've yet to witness a starship rattling like a car on a dirt road from quantum fluctuations, the foam's real-world effects, like the Casimir force or holographic entropy, prove spacetime isn't the serene void we once imagined. Sci-fi just dials it up to 11, giving us a visceral taste of a universe where the fabric of reality is anything but smooth. So the next time you see a spaceship bucking wildly on screen, remember, the writers might be closer to reality than you think. Behind the special effects lies a wild, untamed frontier of physics, where every tremor and time glitch whispers of the quantum foam's unruliness, and who knows? If humanity ever builds warp drives, we might find ourselves white-knuckling through that same cosmic storm. Stretched across the galaxy like cosmic metronomes, millisecond pulsars spin with such perfect regularity. Their pulses arrive on Earth with precision rivaling atomic clocks. These ultra-dense stellar remnants, collapsed cores of once mighty stars, beam radiation across space like interstellar lighthouses, each rotation sweeping a flash of light past our telescopes. But what if these impeccable timekeepers could reveal spacetime's hidden graininess? Astronomers now use their rhythmic flashes as probes to hunt for quantum foam's faintest tremors, turning pulsars into nature's ultimate microscopes. Picture a lighthouse beam cutting through thick fog. On a clear night, the light appears steady, but add turbulent, swirling mist, uneven air, and the beam flickers unpredictably. Now replace the lighthouse with a pulsar and the fog with quantum foam. If spacetime at Planck scales is truly frothy, those ultra-fast pulsar beams should scatter ever so slightly as they traverse billions of light years, their ultra-sharp pulses gaining tiny delays or distortions. It's like trying to shine a laser pointer through a glass of sparkling water. The beam remains mostly intact, but close inspection reveals subtle shimmering from the bubbles. The hunt for these anomalies relies on patience and precision. Teams using radio telescopes like the Arecibo Observatory before its collapse and the Parkes telescope have spent decades cataloging pulsar arrivals, comparing them against theoretical models. The fastest pulsars, spinning hundreds of times per second, are especially valuable. Their pulses are so brief, any deviation caused by spacetime's granularity would stand out like a scratched record in a symphony. Even a Planck-length hiccup in the foam could delay a pulse by a few quadrillionths of a second, a minuscule effect, but one that advanced signal processing can potentially tease from the noise. One tantalizing candidate emerged in observations of pulsar J433-7145. Its pulses showed faint, repeating irregularities that some researchers argued could be signatures of foam-induced scattering. Skeptics countered that interstellar plasma or instrument glitches could mimic the effect, but the debate highlights pulsars' potential as probes. Future telescopes like the Square Kilometre Array, with its unparalleled sensitivity, could settle the question by analyzing thousands of pulsars simultaneously, mapping spacetime's texture across the cosmos. The beauty of this method lies in its cosmic scale. While particle accelerators like the LHC smash matter to study the infinitesimally small, pulsars leverage the universe itself as a laboratory. Their light has traveled through eons of quantum foam, accumulating whispers of turbulence we can now attempt to decode. Each precise tick of these stellar clocks isn't just a time signal, it's a message from the void, etched with the secrets of spacetime's stormy depths. And if the foam is truly there, its fingerprints might finally be revealed in the quiet irregularities of a pulsar's unchanging beat. While quantum foam paints spacetime as a churning sea of chaos, loop quantum gravity offers a radically different vision, one where the universe isn't a turbulent storm, but a vast, shimmering spiderweb of interwoven threads. Picture an infinite tapestry where every fiber pulses with energy, constantly reconfiguring itself like a cosmic neural network lighting up with each new thought. This isn't just a poetic metaphor, it's the backbone of a theory that replaces the foam's disorder with something startlingly elegant. Spacetime built from indivisible, glowing strands, each just a Planck length thick. Imagine zooming in on the fabric of reality until atoms look like planets. Instead of finding foam, you'd see a dynamic lattice. Think of a mesh screen flexing and twisting, its intersections flickering like fireflies as they exchange energy. These aren't passive threads, they're the universe's DNA, encoding everything from the spin of electrons to the curve of galaxies. Where quantum foam suggests spacetime is a boiling soup, loop quantum gravity argues it's more like a vibrating guitar string, with every note corresponding to a different particle or force. The theory's brilliance lies in how it sidesteps the foam's infinities. Just as a digital photo can't be zoomed beyond its pixel resolution, spacetime in this model can't be divided beyond the Planck length. No black holes from overzealous measurements, no singularities where physics breaks down, just a seamless network where gravity emerges naturally from the dance of these threads. It's as if the universe runs on cosmic code, with spacetime itself updating in discrete, rhythmic steps rather than continuous flow. Critics once dismissed this as mathematical fantasy, but recent simulations show something astonishing. When you model the Big Bang using loop quantum gravity's framework, the equations don't explode into nonsense at time zero. Instead, they suggest a bounce, a moment where collapsing spacetime rebounds like a compressed spring, possibly explaining what came before our universe. No foam, no singularity, just an eternal reweaving of the cosmic web. Yet for all its order, this web isn't rigid. Black holes, for instance, might be knots where threads tangle so tightly they temporarily pin spacetime into a vortex. And dark energy could be the threads stretching as the universe expands, each fiber thinning like pulled taffy until its tension starts pushing galaxies apart. Even time loses its smoothness here, not a river, but a flickering sequence of frames, each a snapshot of the web's latest configuration. The starkest contrast to quantum foam lies in the details. While foam predicts microscopic black holes and wormholes blinking in and out of reality, loop quantum gravity sees spacetime as fundamentally sturdy, just pixelated. It's the difference between building with Legos and building with smoke. One clicks together with precision, the other swirls unpredictably. Both theories agree reality has a smallest scale, but they clash violently on what happens there. What makes this more than abstract physics is the potential for validation. If spacetime is truly a woven network, then future gravitational wave detectors might catch subtle hiccups in their signals, evidence of the web's granularity. Or perhaps quantum computers could simulate the thread's behavior, revealing patterns hidden in the noise. Until then, the theory stands as a testament to human imagination. A universe not of chaos, but of luminous connections, humming with the quiet music of geometry itself. What if the same chaotic swirl that underlies spacetime also flickers inside your mind? Some theorists propose a radical idea. The quantum foam's turbulence might not just shape the cosmos, it could play a role in the very fabric of consciousness itself. Picture this: a neuron fires in your brain, its synaptic vesicles releasing neurotransmitters in a burst of activity. Now zoom way in until the boundary between neuron and void blurs. At scales approaching the Planck length, could the brain's electrical storm be interacting with spacetime's frothy depths? The notion isn't entirely far-fetched. Compare an electron microscope image of synaptic networks to an artist's rendering of quantum foam. Both are webs of frenetic activity, flickering connections appearing and vanishing in fractions of a second. Some models in orchestrated objective reduction theory, pioneered by physicist Roger Penrose and anesthesiologist Stuart Hameroff, suggest microtubules, tiny protein structures in neurons, might harness quantum vibrations. These vibrations, dancing at the edge of spacetime's turbulence, could theoretically collapse into conscious moments, like foam bubbles bursting into observable reality. Of course, this pushes mainstream neuroscience to its limits. Critics point out that the warm, wet environment of the brain should destroy delicate quantum states faster than they can form, a phenomenon called quantum decoherence. But proponents counter with examples from nature. Photosynthesis relies on quantum coherence in plant cells, and migratory birds navigate using quantum-entangled molecules in their eyes. If biology can exploit quantum effects in these systems, why not the brain? Then there's the brain as cosmos metaphor. Neural networks and the cosmic web of galaxies share eerie structural similarities, filaments of matter and synapses both forming clustered nodes amid vast emptiness. Could the quantum foam be the hidden thread connecting micro and macro, its patterns echoing across scales? It's a poetic idea, though skeptics argue similarity isn't causation. The most tantalizing and controversial implication: if consciousness somehow taps into the foam's turbulence, subjective experience might not be confined to the skull. Philosopher David Chalmers once pondered whether information itself has an experiential quality. Extend that to the foam's ceaseless computations, and you're flirting with panpsychism, the notion that even particles might harbor whispers of awareness. For now, these ideas live at science's outer edges, but they force us to ask bigger questions. Is the universe's chaotic foundation just passive backdrop, or an active participant in perception? As we map both neural circuits and spacetime's granularity, perhaps we'll find they're not separate puzzles, just different facets of the same enigma, shimmering like foam on a dark cosmic sea. There's a hidden danger lurking in the quantum foam, one so catastrophic it could rewrite the universe in an instant, not with a bang, but with a silent, unstoppable wave. Picture dropping ink into a glass of water. At first, it's just a tiny dark cloud swirling lazily, but then it spreads, overtaking the clear liquid molecule by molecule until the entire glass is stained. Now imagine that ink is a new set of physics, and the water is reality itself. This is the nightmare scenario physicists call vacuum decay, a theoretical reality wipe born from the quantum foam's infinite unpredictability. Here's how it could happen. The universe as we know it sits in what scientists call a false vacuum, a stable but not perfectly stable state, like a marble resting in a shallow dent on a hillside. It seems solid, but given the right nudge, it could start rolling downhill into a deeper, truer minimum. That nudge might come from a random quantum fluctuation in the foam, a tiny bubble where the laws of physics briefly flicker into a new configuration. If that bubble forms with just the right conditions, it could expand at the speed of light, rewriting the vacuum around it as it goes. The wave front wouldn't just destroy matter, it would redefine existence, altering fundamental constants like the strength of gravity or the mass of electrons. Stars, planets, even atomic bonds would unravel in its path, replaced by a new reality with rules we can't begin to predict. The terrifying beauty of this scenario lies in its inevitability once triggered. There'd be no warning, no time to react. One moment, everything is normal. The next, an invisible wall of transformation sweeps through the cosmos, leaving nothing familiar in its wake. It's not an explosion or a collapse, it's a quiet, surgical overwrite of reality itself. The scariest part, some calculations suggest this might have already happened elsewhere in the cosmos, with the wave front racing toward us at light speed, undetectable until it arrives. Yet there's a twist of cosmic irony here. The very instability that could doom us might also be the reason we exist at all. If the universe's vacuum were perfectly stable, the primordial quantum foam might never have produced the asymmetries that led to matter dominating antimatter, or the fluctuations that seeded galaxies. Our reality is, in a sense, built on a knife's edge between stability and chaos, a precarious balance that allows life to flourish, even as it teeters over an abyss of annihilation. So while the odds of vacuum decay are astronomically low, perhaps once in a Google years, it's a haunting reminder that the quantum foam isn't just a scientific curiosity. It's a cosmic wildcard, capable of both creating and erasing worlds with the same indifferent flicker. The same froth that birthed the stars could one day unmake them, not with fire or ice, but with a ripple in the dark. The same quantum foam that twists spacetime at unfathomably small scales might be quietly revolutionizing the machines in your local hospital. Hidden within the sleek, humming chambers of MRI scanners lies an unexpected connection to this turbulent subatomic realm. These life-saving devices rely on superconducting magnets chilled to near absolute zero temperatures so extreme, they mute even the restless flickering of virtual particles in the quantum foam. It's this suppression of spacetime's chaos that allows MRI magnets to maintain their flawless magnetic fields, capturing razor-sharp images of the human body. Without the foam's influence being tamed, those detailed brain scans or spinal cord images would blur into useless static, as if trying to photograph a moving target through frosted glass. Now shift your gaze from hospital basements to cutting-edge quantum labs, where scientists wrestle with the foam's turbulence in a different battle, the race to build stable quantum computers. Unlike classical bits that obediently sit in 0 or 1 states, quantum bits qubits exist in delicate superpositions, balancing probabilities like a spinning coin mid-toss. The problem, the quantum foam's ceaseless churn introduces microscopic noise, nudging qubits out of their fragile states like gusts of wind toppling a house of cards. But researchers are fighting back with ingenious solutions. In lab close-ups, you'd see qubits shielded in elaborate electromagnetic cages or embedded in materials that smooth out spacetime's roughness at critical scales. Some designs even leverage the foam's randomness, using error-correcting algorithms that treat quantum noise like static in a radio signal, something to filter rather than defeat. The real breakthrough came when teams realized the foam's fluctuations aren't pure chaos, they follow statistical patterns. By mapping these patterns, engineers can now predict and counteract disruptions, pushing qubit coherence times from microseconds to milliseconds. That might sound trivial, but in quantum computing, it's the difference between a calculator that crumbles mid-equation and one that solves problems no classical machine could touch. The same principles are even refining atomic clocks, where spacetime's granularity introduces tiny timing errors. By accounting for the foam's tremors, these clocks now keep time so precisely they'd lose less than a second over the entire age of the universe. So while quantum foam might seem like an abstract curiosity, its fingerprints are everywhere, from the medical diagnostics saving lives to the encrypted communications shielding our data. The next time you hear an MRI's rhythmic thumping or read about a quantum leap in computing, remember, it's not just human ingenuity at work. It's our growing mastery of spacetime's hidden storm, learning to sail where once we could only struggle against the current. High above Earth's atmosphere, NASA is preparing to launch a telescope with an extraordinary mission to hunt for the faintest traces of spacetime's ultimate fuzziness. The Gamma-Ray Large Area Space Telescope, or GLAST, isn't just another satellite scanning the cosmos. It's a quantum detective armed with sensors so precise they could spot the subtlest shimmer in gamma-ray bursts, potential fingerprints of the quantum foam's turbulent dance. Imagine tuning a radio to static, then suddenly catching a faint, rhythmic distortion buried in the noise. That's what scientists hope to find in the high-energy light streaming from distant black holes and neutron stars. Here's how it works. When gamma rays traverse billions of light years to reach us, they should, in theory, arrive at slightly different times depending on their energy. Higher energy photons might interact more strongly with the foam's microscopic bubbles, as if trudging through deeper snow. If spacetime were perfectly smooth, like a pane of glass, all photons from the same burst would travel in lockstep. But if quantum foam exists, the highest energy rays could lag behind by mere attoscons, billionths of a billionth of a second, staggered by spacetime's hidden texture. GLAST ultra-sensitive detectors are designed to catch these minuscule delays, turning gamma-ray bursts into cosmic yardsticks measuring the universe's graininess. Concept art of the mission shows the telescope silhouetted against a star field, its solar panels gleaming as it locks onto a brilliant burst. In the data stream, physicists will search for patterns resembling static on an old TV, not random noise, but the telltale fuzz of Planck-scale spacetime bubbles leaving their mark. Some models suggest these fluctuations could scramble gamma-ray polarization, twisting the light's orientation like a message passed through a hall of warped mirrors. Others predict spectral distortions, as if the foam acts like a celestial grater, shredding light into unexpected wavelengths. But the real magic lies in what GLAST can't see. If quantum foam disrupts spacetime severely enough, it might impose a fundamental limit on how sharp distant bursts appear. Like trying to project a movie onto a frosted window, the images could blur at energies approaching the Planck scale, revealing where the universe itself runs out of resolution. It's a paradoxical hunt, using the brightest explosions in existence to illuminate the darkest corners of physics. Of course, skeptics argue that interstellar gas or magnetic fields could mimic these effects. That's why GLAST won't work alone. Its data will cross-check against neutrino observatories like IceCube and gravitational wave detectors like LIGO, creating a multi-messenger map of spacetime's hidden terrain. If all three instruments see consistent anomalies, the case for quantum foam strengthens dramatically. The stakes couldn't be higher. Success would rewrite textbooks, proving that Einstein's smooth spacetime is an illusion, a statistical average of unimaginable chaos beneath. Failure, though, might be just as revealing. If GLAST finds no trace of fuzziness, it could hint that spacetime's structure is stranger still, woven from loops or strings rather than froth. Either way, the telescope's findings will ripple through physics, from black hole thermodynamics to theories of quantum gravity. So when GLAST beams its first data back to Earth, It won't just be capturing gamma rays, it'll be snapping a photo of reality's fabric, closer than we've ever seen before. And somewhere in those shimmering pixels, the quantum foam's secrets may finally develop, like an image emerging in a darkroom tray. If the universe is built on a foundation of chaos, a seething quantum foam where particles blink in and out of existence and space-time itself stutters, then what does that mean for the very idea of cause and effect? We like to think of reality as a chain of orderly events. A ball rolls because someone kicked it, a fire burns because someone struck a match. But at the Planck scale, where the foam's turbulence reigns supreme, those tidy rules might not apply. Picture a pair of dice tumbling in zero gravity, colliding with invisible quantum fluctuations. Their paths unpredictable not because of hidden variables, but because randomness is woven into the fabric of existence itself. This isn't just a thought experiment. Physicists grappling with quantum mechanics have long wrestled with the notion that at fundamental levels, the universe might not play by deterministic rules. In the macro world, we see clear causes and effects. Drop a glass and it shatters. But zoom in far enough and the foam's chaos introduces a strange looseness to those connections. A radioactive atom decays not because of some hidden trigger, but because probability dictates its time. A virtual particle pair appears spontaneously, borrowing energy from the vacuum without any prior cause. If these phenomena aren't just exceptions but hints of a deeper truth, then causality as we know it might be an illusion, a statistical mirage emerging from countless chaotic interactions, like the smooth curve of a coastline that up close is nothing but jagged, crashing waves. The implications ripple outward. If causality is porous, then free will, already a philosophical minefield, gets even messier. Are our choices truly ours, or are they the end result of quantum fluctuations cascading through the foam, nudging neurons one way or another? Even time's arrow, that unshakable march from past to future, might falter in the foam's turbulence. Some models suggest that at Planck scales, cause and effect can briefly reverse, like eddies in a river flowing upstream. It's as if the universe's clockwork has tiny, chaotic gears, occasionally slipping out of sync. Yet here's the paradox: despite this underlying randomness, the large-scale universe appears astonishingly orderly. Galaxies rotate with precision, chemical reactions follow predictable paths, and the laws of thermodynamics hold firm. How does structure emerge from chaos? One compelling answer lies in something called decoherence, the idea that while quantum systems might start in fuzzy, probabilistic states, their interactions with the environment collapse them into definite outcomes. It's like the foam's turmoil being smoothed out by sheer scale. The way a spinning coin eventually settles into heads or tails. The dice might tumble wildly in zero gravity, but once they hit the table, their randomness is resolved into a single, observable result. This tension between chaos and order raises even deeper questions. If reality is fundamentally indeterminate, why does it feel so solid? Some physicists speculate that causality isn't a law of nature but a cognitive shortcut, a story our brains tell to make sense of a universe too complex to process. Others suggest that the foam's randomness is constrained by deeper symmetries, like a storm contained within the walls of an invisible labyrinth. The truth might lie somewhere in between, a cosmos that's neither fully deterministic nor entirely lawless, but a dance of probability and pattern, where every moment is a negotiation between chaos and structure. So the next time you watch a ripple move across a pond or trace the arc of a thrown ball, remember what looks like straightforward cause and effect might be the surface illusion of a far wilder reality. The quantum foam doesn't just underpin the universe, it quietly challenges our most basic assumptions about how things, and perhaps even we ourselves, truly work. Let's try something wild. Close your eyes and picture yourself standing at the edge of a pond, except this pond isn't filled with water. It's a seething, bubbling expanse of quantum foam, each bubble a fleeting distortion of spacetime itself. Now imagine you have to cross it. Your path isn't solid ground but a series of unstable stepping stones, each one a Planck-length bubble that might pop or warp beneath your feet without warning. In this mind-bending scenario, every step would be a gamble. Lift your foot to move forward, and the bubble you're standing on might dissolve mid-stride, leaving you momentarily suspended over a void where space-time itself stutters. Your next step lands on a new bubble, but this one wobbles unpredictably, as if the very concept of surface tension is negotiable. The rules here aren't just different, they're fluid. One moment, gravity might feel normal. The next, your foot could sink slightly into the bubble as if space itself has the consistency of gelatin. Now, picture a stick figure attempting this crossing in slow motion. As it hops from one bubble to another, some vanish in flashes of virtual particles. Others stretch like taffy, distorting the figure's trajectory mid-jump. Occasionally, a bubble might briefly tunnel into a microscopic wormhole, causing the stick figure's leg to momentarily disappear before reappearing a fraction of a millimeter off course. It's not just walking, it's navigating a reality where the ground isn't just unstable, but actively rewriting the rules of what ground even means. This isn't pure fantasy. Physicists grapple with these extreme conditions when probing the Planck scale, where spacetime's smooth geometry shatters into chaos. Your thought experiment captures why merging quantum mechanics and general relativity feels like building a bridge out of smoke. Every theoretical stepping stone, every equation, every model, either dissolves under scrutiny or warps into something unrecognizable. But here's the twist: this instability might be the universe's creative engine. Just as your stick figure's path isn't predetermined, the foam's turbulence could be why particles pop into existence, why black holes radiate, even why the cosmos has structure at all. Chaos, it turns out, might be the price of a universe that's dynamic rather than static, a cosmos where crossing the pond isn't just possible, but where the act of crossing changes the pond itself. So the next time you walk across a stable floor, take a second to marvel at the illusion of solidity. Beneath your feet, in a realm too small to see, the ground is anything but steady. It's a dance of creation and destruction, where every step you don't sink is a minor miracle of emergent order. And if you ever feel like reality is fixed and predictable, remember the stick figure hopping through the storm, where every landing is a leap of faith. Zooming out from the Planck scale maelstrom of quantum foam, we're left with a startling realization. The universe isn't just stranger than we imagine, it's stranger than we can imagine. Every moment of stillness, every predictable sunrise, every solid object we touch is an illusion woven from chaos. The chair you're sitting on, the device in your hand, they're not just collections of atoms, but temporary gatherings in a cosmic storm, flickering against the backdrop of spacetime's endless turbulence. This invisible froth, once dismissed as mathematical abstraction, now stands as the scaffolding of reality itself, shaping everything from the spin of electrons to the fate of galaxies. Consider the sheer scale of this revelation. At one end, quantum foam's microscopic frenzy dictates how particles dance and interact. At the other, its echoes ripple through the cosmos, perhaps driving dark energy's relentless push or seeding the structures we see etched in starlight. Black holes might store their secrets in its fleeting wormholes, while time itself could stutter in its depths. The universe isn't merely built on this chaos, it's of it, a grand tapestry stitched from threads of probability and uncertainty. Carl Sagan once said we're made of star stuff, remnants of exploded suns forged in stellar furnaces. But dig deeper and the story grows even more profound. We're not just star stuff, we're foam stuff, creatures of spacetime's quantum storm, our very existence hinging on the delicate balance between turbulence and order. Every thought, every heartbeat is a rebellion against entropy, a fleeting pattern in the foam's infinite churn. As the camera pulls back from foam to galaxies, remember this: reality's solidity is a beautiful deception. Beneath the surface, the universe thrums with creativity, rewriting itself at every instant. And that's the true gift of quantum foam. Not just a new set of equations, but a lens to see the cosmos anew. If this exploration left you craving more, hit subscribe. We're just scratching reality's quantum cracks, and the next dive will take us even deeper into the storm. Until then, keep looking closer. The ordinary is anything